We continue by doing some examples. We do examples now that are definite. So 35, from 0 to 2, ex over 1 plus e2x dx. See, again, I want you to notice the difference between this and this. See, this, if we want to look at what we just solved together, this is not, of course, formula sheet. We don't have anything in the formula sheet that looks exactly like this. It cannot be simplified because the denominator is made more than one term. So I start thinking it's a fraction. Fractions, first we think about logarithms. So if we want to try logarithms here, what's the derivative? If this is f, the derivative of 1 plus e2x is 2e2x. So it does not work as a logarithm here. So what do we have to think about? Tan inverse. How does tan inverse work? 1 over 1 plus u squared du is tan inverse u plus c. So over here, we want to call this as u squared, not u. Then u is e2x over 2. Dayman, when you want to get the square root, you divide by 2 or you multiply by half. So this becomes ex. Then what is du? Ex dx. Perfect for our problem. So it becomes ex dx is du over 1 plus u squared. But see, since it's a definite integral, what is the one extra step that you have to do? You have to use this to find what the values of u are. So when x is 0, u is e to the power 0, which is 1. When x is 2, u is e to the power 2, which is e to the power 2. Cannot be simplified. So now it changes from 0 to 2 becomes from 1 to e squared. So it becomes tan inverse u evaluated from e squared to 1, which is tan inverse e squared minus tan inverse 1. Tan inverse e squared cannot be simplified, so we keep it as is. Tan inverse 1 is pi over 4. And this is the answer. Now look at the example number 36. It's not formula sheet. I cannot simplify. I start thinking u du. It's a fraction. The first thing I think of is f prime over f. I check it. If f is 1 plus ex, what's the derivative of 1 plus ex? Ex. So this by default does not require any substitution u du. It's ln 1 plus ex. This is in terms of x or u? X, because I didn't change to u, so I keep the limits of x. So it's ln absolute value of 1 plus e squared minus ln absolute value of 1 plus e to the power 0. This is ln 1 plus e squared does not need an absolute value, minus ln 1 plus 1, 2. Ln a minus ln b can always be written as ln a over b as a simplified answer. So do you see how it can work as a logarithm and as a tan inverse problem? Just by a little bit of change. Look at number 37. I'm not going to do the whole thing. I'm just going to state that cotan x, just like tan x, it's written as cosine over sine. Cosine is the derivative of sine, so this is f prime over f, so it's ln absolute value of sine x plus c. And so if you want, you can, if this is limit from pi over 4 to pi over 2, I didn't use any u or anything, so I just canceled the c, pi over 2, because I kept everything in terms of x. I use limits of x. So this is ln sine pi over 2, which is 1, minus ln sine pi over 4, which gives me sine pi over 2, 1, ln 1, 0, sine pi over 4, root 2 over 2. So the answer is minus ln root 2 over 2. This can be simplified because the minus outside ln can come inside when you reciprocate. So this can become ln 2 over root 2. The minus goes inside and reciprocates the answer. 2 over root 2 is root 2 only. It can be written as ln in the simplest possible fraction form. I'm solving as many exercises as can just for you to get exposed. But of course, try to solve them again and again and again to get used to the problem. What is something we always related? Always. So this can be written as, so if u is ln x and du is 1 over x dx, then this becomes u du. What is the only thing we have to change now? The limits. See, if x is equal to 1, u is equal to ln x equals to 0. If x is equal to e, u is equal to ln e, which is 1. So it becomes from 0 to 1. The antiderivative of u is u squared over 2, which is 1 over 2 minus 0 over 2, 1 over 2. This is definite integrals. I'm trying to find if there's anything else I want to cover. Actually, what I want to cover more in this session before I end is I want to skip to section 4.7. We do not cover it. I want to skip to section 4.8. We do not cover 4.8 a lot, but 4.8 just I want to skim through it. What is really important for me is the exercises in the end, but just skimming through 4.8, what does it say? You know, how do we define logarithms? We defined ln y to be the inverse of the exponential. So we defined log base a of u to be b, which means that u is equal to a to the power b. It's exponential, something like that. There is another way where mathematicians defined logarithm, the natural logarithm. They defined the natural logarithm ln to be nothing but the integral from 1 to x of 1 over t dt. They defined it when x is positive. It's just another definition. So either you define it as the inverse of the exponential function. Other sets of mathematicians define it as the antiderivative of 1 over t dt. Perfect? When you define it like this or like this, the beauty is that this ln I'm talking about and this ln have the same properties and have the same answers and have the same values and so on. So they are equivalent functions. That's the only thing extra that they show in section 4.8. I don't cover anything other than that. I want you to directly jump into problems of section 4.8. So I don't want you to do a lot. Problems of section 4.8 from number 1 to 4, numbers 9 to 12, 1 to 4, 9 to 12. All of these are just, what do we call them? Revision of prep program. So I'm not going to solve, of course, any of them. But number 13 to 20 is a revision on derivatives of logarithms and on logarithmic differentiation. So it's good to revise them also. What I'm going to solve only, those are revisions, so I'm not going to solve. You solve them. You solve them. For me, I'm only going to solve from numbers 21 to 30. All right? So number 21, the antiderivative of 1 over x ln x dx. Again, whenever I see ln x and 1 over x, I get that feeling, right? I get the substitution feeling that ln x is u, du is 1 over x. So this changes this into 1 over u, and 1 over x dx is du. What's the antiderivative of 1 over u? Ln absolute value of u. But what is u? It's ln x again. So it's ln x plus c. Another example. Antiderivative of 1 over root 1 minus x squared sine inverse x dx. Again, this is 1 over root 1 minus x squared, 1 over sine inverse x. See, u is sine inverse x and its derivative is 1 over root 1 minus x squared dx. So this becomes 1 over u, and 1 over root x squared 1 minus x squared dx is nothing but du. So this gives me ln absolute value of u, which is ln absolute value of sine inverse x plus c. 23, 24, I don't want to cover, which are exponentials, not of base e. I only want to cover exponentials base e. We solved this already. If u is 2 over x, du will be minus 2 over x squared. So minus 2 minus half becomes minus half eu. Minus 2 over x squared dx is du. So this is minus half eu plus c. So it's minus half e to the 2 over x plus c. 26. Antiderivative of sine ln x cubed over x dx. Students say, you told us ln x and 1 over x relate, but how about ln x cubed? Remember, what is the derivative of ln x cubed? If u is ln x cubed, ln x cubed is 3 ln x. So again, the derivative is 3 times 1 over x. So whether it's ln x cubed or ln x alone or ln x squared or ln root x or ln any power of x, what is the derivative? N times 1 over x dx, because this is written as n ln x, and then the derivative will be n times 1 over x dx. So this is nothing but antiderivative. So 3 times 1 over x, so I want 3 and 1 over 3. Sine u, 3 over x dx is du. What's the antiderivative of sine u? Cosine u, cosine ln x cubed plus c. They're nice. When you start getting the hang of them, they're very nice. 27 is very simple, not going to do it. 28. I think will be 28. Antiderivative 0 to 1 x ex minus e minus x over ex plus e minus x dx. Is formula sheet? No. Can we simplify it? No. It's a fraction. The first thing I think of is the upper, the derivative of the bottom. What's the derivative of ex plus e minus x? The derivative of ex is ex plus minus e minus x. Oh, so it's up. So this is u prime over u. So this is nothing but ln f of x from 1 to 0. I substitute 1, I get minus. I substitute 0, I get this. So this is ln e plus 1 over e minus ln e0 plus e0, 1 plus 1, 2. I can write this as ln e plus 1 over e over 2, because minus becomes division, and these are always plus, so I can drop the absolute value. So it's e over 2 plus 1 over 2e. 29 is the antiderivative of tan x. We've already talked about it. And 30 is ln x over x. We also talked about it. Let me do number 30 one more time. From 1 to 2, ln x over x, which is 1 over x times ln x dx. We let u be ln x. Then du will be 1 over x dx. The moment I have limits, x equals 1, u is ln 1, which is 0. X equals 2, u is ln 2. So this becomes from 0 to ln 2 of u. 1 over x dx is du. What's the antiderivative of u? Many students forget. The antiderivative of x is x squared over 2. The antiderivative of u is u squared over 2, which is ln 2 squared over 2 minus 0 squared over 2, which is 0. So it's ln 2 over 2. So this is what I want from section 4.8. So this covers section 4.6 and 4.8. What we have left in Math 111 is chapter 5, which is 5.1, 5.2, and 5.3. Best regards.